Hi, I'm going to attempt to finish up some of the notes that we haven't quite finished in class. I apologize for the wait. So let's just kind of look at what we have going. Okay, so after 3.6 and 3.7, we move into 3.7 and it's about the chain rule. So I'm going to go back to these notes real quick and see if there's a few things that we might want to do for practice prior to our test. So basically, we had this challenging problem where we had a product of three things, and basically you put two of them together and do the product rule, and then you do the second. So you kind of have to think about this as theta, cotangent theta is one thing, and then do your 1 d2 plus 2 d1. And so when you finally do this d1, you're actually doing another product rule. And I'm just going to emphasize that if I give you a problem like this, you're welcome to just apply all the derivatives and leave it in that form. Okay, so then we did write the equation of tangent lines. I would think this would be something everybody should be able to do. And that was just review. We went into talking about the chain rule, and you have to think about what's on the interior as you do these. So hopefully there's a couple we can discuss. And so we did a few in terms of u, where you choose the u and write it in terms of u. And so if you do that, you're writing y equal u to the 7th, where 3x squared plus 5 is u in terms of x. The derivative of u in terms of x is 6x. Okay, so if you were to go and do the derivative, you would get 7u to the 6th multiplied by du dx, which puts it in terms of x. So you're actually taking your u value, plugging it back here after you've differentiated, and then multiplying by the derivative. So we do a lot of these without writing all those steps. Just remember, if you ever get confused, you can go out to the side and do that. So on our class, we went, this is u is the interior part. So we're actually doing 5 times all that stuff to the 4th times the derivative of the interior, and we're done. Okay, this is the alternative method where you'd have u to the 5th, which means the derivative of u with respect to x would be 5u to the 4th times du dx, which means that you need the derivative of u with respect to x. So you would plug that back in and plug it back in like that. So you can go through that method. I left my 4 off. Okay, so we did some of these. I'm going to turn over. We got to a couple here that we didn't quite finish. Okay, so we also need to know all of our derivatives for sine, cosine, tangent, cotangent, cosecant, and secant. And remember, these come in pairs. So the derivative of sine is cosine. The derivative of cosine is negative sine. So as you do these, remember the signs are opposite. So when you do the derivative of tangent, get secant squared. The co-functions are the ones that are negative. That's one way to remember that, okay? So let's go to G. If you'd like, you can pause the video and try G and I and maybe K. And even the last one. And I'm going to begin shortly. Okay, so hopefully you pause the video to try these first. Okay, so let's go back to G. If I want the derivative of cosecant, first I have to have it memorized, which is negative cosecant cotangent, and we've got to put this in terms of x. So we're going to go negative cosecant of this thing, or u, cotangent this thing, and that is our derivative without doing the interior. So then the interior part would be times the derivative of the u, which is 35x to the 4th. So remember that this is times 35x to the 4th. Just make it clear that this is multiplied by the cotangent and not just that. Okay, so that's your derivative, and you can leave it like that. Okay, this one actually has three parts. Notice this is the power rule, the derivative of the trig function, then the derivative of the angle. So I'm giving you a descriptor right above these. So if you were confused, you're thinking about x squared here. So it's 2 times that secant thing, subtract 1, okay? So you're going to have 2 times the function, subtract 1 from the 2, you get 1. It's all in terms of 4x cubed plus 5. Okay, so that's the most outer function. I just did the power rule. Now we're going to do the derivative of the secant function because the x cubed part of it is inside the secant. So we're actually doing 3 things here. Now the derivative of the secant function would be secant tangent. Okay. So now we're going to multiply by secant of this thing times tangent of this thing. Oops, 4x cubed plus 5. Okay, so this is the derivative of the secant function in terms of this 4x cubed plus 5. Now we have to go inside the secant function and do the derivative of that inner part. So this would actually be 12x squared, so times 12x squared, okay? And this is clearly not times this piece, but is multiplied by the tangent, secant, okay? So it is possible you could write this with a square, okay? Since they wound up being the same term, okay? Or you can leave it like this. At least you have the idea of it. Now, there is a long way to go through this. I'm just going to kind of show it to you, and if you're trying to process what's going on with it, this might be helpful. Okay, so if you think about the most interior thing, it's 4x cubed plus 5. And the derivative of 4x cubed plus 5 is du dx, which is 12x squared. So if you wanted to rewrite this function as the derivative of secant squared u, then you're going to have to put it back in terms of x later, okay? So if that's the case, then you could also let the secant u be another variable such as v, and we know dv dx would be secant tangent, okay? So this is where we get that we're doing the polynomial first, or the power. So this is just 2v times the derivative of v with respect to u times the derivative of u with respect to x, okay? So we're kind of working our way out. So if you were to do it that way, you'd have to go to secant u, because that's what we let v be, and then you would say dv du is secant u tangent u, but then you have to put the u's back in, which is the 4x cubed plus 5 and multiply by du dx. So that's a very long way to go through that, but that kind of shows you how everything lays out, okay? So with that said, let's go on and try k. Okay, on k, on this problem, you're doing a second derivative, which means you're going to begin with, or did I skip k? Okay, so let's go to k. K is h is f of g. Find the derivative of h at 3. So this is a composition function, which means you're doing f prime of g of x times the derivative of g of x. And we're doing this all in terms of the number 3. So if I come over here and make this 3, then I need g of 3 on the inside right here is 2. So this is actually f prime of 2 times g prime of 3 g prime of 3 is negative 5. And f prime of 2 is not there. So did I make a mistake? Okay, g of 3. G of 3. So what's f of g? Do we know f of g or f prime g of 3? What's g of 3? Oh, I made a mistake. Oh, here it is. G of 3 is 4. Huh. So I looked at it wrong. This is a 4. Here. Here. Okay, now f prime of 4 is 8. So this is 8 times negative 5, negative 40. Okay, so you could count on having a problem where you're given a bunch of stuff and you have to come up with the value based on the stuff. Okay, the second derivative of this, okay, again, pause if you haven't. All right, this would be 3 times 4 is 12 times this thing on the inside squared times the derivative of the inside, which is 2x. This is the first derivative. I want the second derivative, which means that, okay, so that again was 12 subtract 1 times the derivative of the inside. If I have to take another derivative, I probably want to rewrite this as 24x times x squared minus 5 squared. That way I only have to deal with 2 different things multiplied. So this would then be the second derivative. 1d2 plus 2d1 is what I'm doing. First times derivative of second plus second times derivative of first. So first, the derivative of the second is 2 times this stuff times the interior 2x plus, okay, so this is 1 d2 plus, and I got to write down 2, and d1 is 24. Okay, and you can actually leave it like that, okay, even though I would like it simplified, but we'll leave it like that, because that way if you mess up, you don't lose points. Okay, so let's go on to here. And if you haven't tried this one, pause it and try it. Find the point where F has a horizontal tangent line. So the process here is to take the derivative, set it equal to 0, because the slope of a horizontal line is 0. So we're going to go F prime of x equals, okay, I'm going to write this as x times 2x minus 1 to the negative 1/2. And I'm doing that just so I can use the product rule instead of the quotient rule. Okay, so now I'm going to go 1 d2 would be negative 1/2 2x minus 1, subtract 2 over 2, which is subtracting 1, gives me negative 3 over 2. Okay, so that's my 1 d2 plus 2, which is this piece, all right, d1 would be 1, the derivative of x. Okay, so there's my first derivative. Now that I need to set equal to 0 and solve, because I want my derivative to equal 0. So because I'm looking for the point where the horizontal tangent line is at. So now, how would I clean this up a little bit? Let's see. I could rewrite all of this as negative x over 2 times, we have not done this problem, 2x minus 1 to the positive 3 over 2, okay, plus 1 over 2x minus 1 to the 1/2, okay. I need this to equal 0. So generally you would have a common denominator at this point. Okay, so this isn't very pretty. So what you would do is if I multiplied the bottom of this thing by 2x minus 1, I would actually have a common denominator. So let's see if that does it. Okay, so this is giving me a common denominator. And so basically I multiplied by 2x minus 1 over 2x minus 1 so that I could add these exponents to get 3 over 2, which means that I now have negative x plus 2x minus 1 over this. Okay, I'm out of space, so I'm going up there. Okay, so I have negative x plus 2x minus 1 over this denominator, 2x minus 1 to the 3 over 2. And I'm setting this equals 0, okay? Because I'm looking for x to be where this happens. So this actually comes out to be x minus 1 over all of this to the 3 over 2, okay? So you can see from this, if I cross multiply, this is going to drop out. And I'm going to have x minus 1 equals 0, so x equal 1. Okay? So once I get x equal 1, I'm going to go back to my function and plug it back in to find that point. So then my y value would be 1 over square root of 2 times 1 minus 1. Which gives me 1 over square root of 2 minus 1, which is 1. So the answer is 1, 1. Okay? So that's kind of some messy algebra, but that actually has to happen for us to do that. Okay? So the video is getting kind of long, and I have a few more examples I want to look at with you. Okay? So I'm going to put these in another video, and I'm going to call it graphical derivatives, okay, and the same section.